For centuries, whenever work had to be done, man was dependent on sheer muscle power. Later, with the help of water wheels and windmills, he was able to utilize the power of the elements, but only to a limited extent. It was not until the early 18th century that a new solution presented itself to those who wished to be independent of the weather and geographical factors. That solution was the steam engine. One name stands for its success story, that of James Watt. This Scottish engineer didn't invent the steam engine, but he vastly improved the original concept. In 1775, Watt and his partner, Matthew Boulton, set up a factory in Soho, today a part of Birmingham, which manufactured modern steam engines for delivery to industrial centres all over Europe. Visitors asked Watt himself about all the latest technical developments. But he wouldn't reveal any details. Indeed, he kept his knowledge a closely guarded secret. Any visitor who made too many sketches, like German engineer Georg Friedrich von Reichenbach, was seen as a spy and quickly shown the door. Watt had acquired his expertise at great effort over many years. James Watt was born in Greenock, near Glasgow, in 1736. His father was a ship's chandler who had his own small workshop. From time to time, he also repaired nautical instruments. James spent a lot of time in his father's workshop, watching him at work. At the age of 18, he started an apprenticeship as a precision engineer in Glasgow, which he completed in London. James learned how to manufacture scientific instruments, and in doing so, provided proof of his talents. In 1756, Watt returned to Glasgow. Since the length of his training did not meet the requirements of the craftsmen's guilds, he was not permitted to set up his own workshop. However, Glasgow University required his services. And in 1757, it allowed him to open up a small instrument-making business on its premises. This was a real stroke of good fortune for Watt. Since staff at the university imparted modern technical knowledge and engaged in research. Its scientists were particularly interested in the steam engine. It enabled heat to be converted into mechanical energy. In 1712, a blacksmith and inventor called Thomas Newcomen had built a practical steam engine. It was designed to improve the efficiency of water pumps in mines so that galleries could be driven further underground. With Newcomen's invention, water is made to vaporize in a boiler. The steam is fed into a cylinder. The pressure from the steam and the weight of the pump rods on the other side of the beam slowly force a piston in the cylinder upwards. The steam supply is now cut off and cold water sprayed into the cylinder. The steam condenses and its volume decreases abruptly. This creates negative pressure in the cylinder and, because of the atmospheric pressure acting from above, the piston moves back down into its original position. The water that is collected in the cylinder is drawn off and the process starts again. For many years, steam engines were used primarily for operating pumps. Newcomen's success was also revealed by the fact that a model of his machine was used at Glasgow University for explaining how steam engines worked. But the model didn't always function as well as intended. When it came to an unexpected stop yet again, it ended up on Watt's workbench for repair. James Watt began to examine a machine that was totally new to him. He discovered that the principle was not very economical, because when the cylinder fills with steam it gets very hot, and when condensation takes place the cylinder cools down considerably. With each working cycle, the cylinder first has to be heated up again, so a large amount of the steam supply is wasted. Is it really necessary, Watt thought, for the cylinder to cool again? Surely leaving it hot would be much more efficient, but in that case, how could the steam be condensed? Watt then had the brilliant idea of using two separate cylinders. At the start of his process, the piston is at the bottom of the cylinder. When steam is introduced under the piston, this subjects it to pressure. As with Newcomen's machine, the pressure from the steam and the weight of the pump rods force the piston upwards. Now the steam supply is cut off and a pipe leading into the second cylinder, the condenser, is opened. In this case too, the cooling of the steam creates negative pressure, which, together with the atmospheric pressure, forces the piston back down. The pipe connecting the cylinder with the condenser is then closed off again and the steam valve opened. The process can now be repeated without the steam cylinder having to cool down. In 1769, Watt had his improvements patented, but in order to build a practical steam engine, he needed a lot of money. He found a financier in John Roebuck, a mine owner. In return for his support, Roebuck claimed a 2/3 share in Watt's patent. But 4 years later, Roebuck went bankrupt. He sold his patent rights to a wealthy manufacturer from Birmingham, Matthew Boulton. Boulton immediately recognized the importance of Watt's steam engine. Shortly afterwards, he and Watt founded the world's first factory for manufacturing steam engines, Boulton and Watt. Only a year later, production got underway. Meanwhile, Watt was already working on further improvements. His aim was to boost the efficiency of the steam engine so that it could be used for other tasks beside operating pumps. He achieved this with his double-acting steam engine. First of all, steam flows into the cylinder and forces the piston downwards. Watt's idea was that when the piston is at the bottom of its stroke, steam pressure could also be used to force it back up. To achieve this, the steam supply is cut off at the top and opened up at the bottom of the cylinder. Steam now flows into the cylinder from below and forces the piston back up, and to prevent steam at the top from impeding the upward movement, the steam supply there is cut off and the connection to the condenser opened. When the piston is at the top of its stroke, the process begins again. The steam supply is opened at the top of the cylinder and shut off at the bottom. At the same time, the connection to the condenser for the superfluous steam is opened. With this technique, Watt was able to utilize both piston movements, upwards and downwards, to achieve a vast improvement in efficiency. The double-acting steam engine was also suitable for converting the up and down motion of the piston into rotary movement. So instead of just pumping water out of mines, the steam engine could also be used to drive other machines as a substitute for wind and water wheels. To achieve this, Watt invented a special transfer mechanism, a planetary gearing. In addition, uniform rotary movement is attained by means of a large, heavy flywheel. But one major problem remained. If several looms in a mill were operated simultaneously, the heavy load caused the speed of the steam engine to fluctuate considerably. To correct this, the steam supply had to be regulated by hand. But in 1788, Watt solved the problem. He developed an automatic speed control, the centrifugal or flyball governor. If the speed of the steam engine increases, centrifugal force causes two rotating masses to move outwards. This motion is transferred to a throttle valve, which reduces the steam supply from the boiler to the cylinder, so the machine again runs at its original speed. Conversely, if the steam engine is running more slowly than normal, the throttle valve opens to raise its speed. It's an automatic control system. In order to describe the advantages of his rotary steam engine in a better way, Watt introduced a measure for its output: horsepower. The work done by horses had been used for this purpose at an early date, but Watt made the comparison more precise. In 1782, he calculated the size of a steam engine for a sawmill. He'd obtained data on the performance of the horses used in it from the miller. On the basis of this, Watt determined that 1 horsepower was the amount of work needed to raise a mass of 75 kilograms 1 meter in 1 second. Through their improvements, Boulton and Watt enabled the steam engine to achieve a breakthrough. Now, it wasn't just mine operators who wanted the new type of steam engine, but also the owners of paper and cotton mills. A few years later, James Watt was a wealthy man. Patent revenues to the tune of more than £76,000 swelled his bank account. And his achievements were soon recognised by Britain's social elite. In 1785, James Watt, a man who had never studied, was made a Fellow of the Venerable Royal Society of London. Watt's steam engine was successful, but the limits of its performance capacity had not been reached. However, Watt's patent rights prevented other engineers from developing steam engine technology any further. They had to wait until 1800, when his patents expired. One step which Watt had always declined to take was the use of higher pressure in his steam engines. But this enabled the construction of smaller and even more efficient machines, which opened up new areas of application. In 1804, Richard Trevithick built a steam engine that could travel on rails. George Stephenson used the concept in designing his locomotive, the Rocket, which in 1829 won a speed and endurance contest near Liverpool. In addition to the railways, it was above all large steamships which used the new engines. James Watt died in Heathfield near Birmingham on August the 25th, 1819. Nearly 200 years on, the man whose developments launched the modern industrial era is still very much present in our everyday lives. Not only in the horsepower unit which he introduced, but also in the watt and the kilowatt, units which have replaced horsepower as a means, for example, of indicating the output of a car engine.